Hi everyone, welcome to Joestat. My name is Dipankar Bera. In the previous video, I discussed concept and applications of principal components. Now I will explain how it works and how to extract principal components from the original datasets. A principal component represents a direction that captures the maximum variance in the data. To find this direction, we compute the best fit axis or line. In other words, to quantify the direction of maximum variance, we compute the best fit line through the data. In general, there are various methods to fit best fit line depending on the objective of the analysis. The most common methods are ordinary least square best fit line, reduced major axis best fit line, perpendicular or PCA based best fit line. In the case of PCA, the primary goal is to maximize the variance and minimize the error along all directions. To achieve this, we use orthogonal or perpendicular best fit lines, which captures the maximum variance and minimize the error across all directions. Perpendicular refers to the fact that the error is measured as the perpendicular distance from the actual data points to the fitted line. We can also call it unexplained variance by this fitted line, the distance between the actual and projected values. This represents the variance explained by the line, which is the distance from the origin to the projected point on the line. This is the total variance of a point, the distance between original and actual values, which remains fixed for that point. Since this forms a right angle triangle, we can apply the Pythagorean theorem here to understand how explained variance and error are inversely related. So here the sum of a square and b square is equal to c square, and a, b are inversely related. That means when a increase, b decrease, and b increase, a decrease. Our goal is to maximize a and minimize b, because a represents the explained variance or variance captured by the fitted line. Now we will practice with two variables to better understand how principal component works and how to extract principal components from the original data. These are two variables, x1 and x2. Standardizing the dataset is crucial processing step to ensure that each variable has a mean of 0 and standard deviation of 1. This process centers the data and reduces the effects of varying scale factors across variables. Like x1 ranging from 0 to 1000 could dominate x2 ranging from 0 to 10. Therefore, standardization of data is needed. Here is the standardized version of the data using the z-score. Now, to get the maximum variance by a fitted line, we have to put a random line from random direction and rotate it until we get the maximum variance or best fit line for all points. Let's put a random line. For this random line, unexplained variance or error for individual values at a perpendicular distance are here. These are projected values for individual actual values. So the individual explained variance are V1, V2, V3 and V4. Actually, we need to square all of them so the negative value don't cancel out positive values, and sum of explained variance is V1 square plus V2 square plus V3 square plus V4 square. This is explained variance by this line. Now rotate the line and measure explained variance. This way we rotate the line until we get the maximum sum of explained variance. Finally, this line explains the maximum variance, so this is best fit line or principal component 1. This line has both a direction and captured variance, that means explained variance. The direction is called eigenvector and variance is used to calculate eigenvalue. Here the direction is measured as the slope of the line, which is measured as a change of vertical distance divided by change of horizontal distance. For example, if the slope of this principal component or best fit line is 0.5, it means that for 1 unit change in the vertical distance, there is a 2 unit change in the horizontal distance. Also, we can say to make this principal component, we need 2 units of variable x1 and 1 units of variable x2. This is called linear combination of variables x1 and x2. The eigenvector is expressed as a unit vector, which means the length of vertical and horizontal distance when the length along the principal component direction is 1 unit. So first we need to calculate length along the principal component and then normalize it to 1. This is a right angle triangle, and if b equal to 1 and a equal to 2, we can apply the Pythagorean theorem to get the length along the principal component. So c square equal to a square plus b square, and then the length along the principal component or c is 2.236. So we can say the length of c is 2.236 when a is 2 and b is 1. To find the value of a and b when the length along the principal component is 1, we divide each component by 2.236. So now length on the principal component is c equal to 1, b equal to 0.447 and a equal to 0.894. So the eigenvector for this best fit line or principal component 1 is 0.894, 0.447. The eigenvalue for a principal component is measured as the average of the explained variance. Eigenvalue of this principal component is the sum of the variance explained by this line divided by n-1. 2.27 is eigenvalue of principal component 1. Now we have principal component 1 with eigenvalue and eigenvectors. Let's work on principal component 2. For the second principal component, we need to find the best fit line that is perpendicular to the first principal component. Since we are working in 2 dimensions with just 2 variables, principal component 2 is simply the line that is orthogonal to principal component 1. In this 2-dimensional case, there is no need for further rotation. Principal component 2 is just perpendicular to principal component 1 and captures the remaining variance in the data. When we have 3 variables, the second principal component is perpendicular to the first principal component, but there are many directions perpendicular to principal component 1. So we need to rotate within that perpendicular plane to find the maximum variance. Then the third principal component is perpendicular to both principal component 1 and principal component 2. These are principal component 1, principal component 2, and principal component 3. And beyond the third variable, we can't visualize. If we have 4 variables or more, we can still extract principal components, and principal components are mathematically orthogonal to each other and captures a portion of the variance in the data. In this way, if we have 20 variables, we can extract 20 principal components mathematically. Now for extracting the values of principal components, let's move to 2 dimensions. These projected points are values of principal components. These are perpendicular to the actual values. These are for principal component 1. Check the table for values. These are for principal component 2. Check the table for values. The total variance of the entire dataset we can calculate as the sum of the eigenvalues of all principal components. The eigenvalue for principal component 1 is 2.27 and for principal component 2 is 0.39. So the total variance is 2.27 plus 0.39 equal to 2.66. So here principal component 1 explains 85% of the variance. Principal component 2 explains 15% of the variance. In other words, principal component 1 retains 85% of the information from the original data and principal component 2 retains 15%. We can plot these eigenvalues. It is known as a script plot. Now let's discuss how many principal components should we keep for further analysis. Let's assume we have extracted 100 principal components for 100 variables. So main question is how many principal components should we keep? The answer depends on the objectives of the analysis. For example, imagine you have an image of a bird. This image has a 500 multiplied by 500 pixels, meaning it has 500 dimensions. 10 principal components, you are storing almost 50% of the original data, and the image is still recognizable as a word. So, if your goal is object identification and reducing the data size, this approach is perfectly fine. But if your goal is predictions using machine learning models, regression analysis, maximizing the retained information from the original data is crucial for improving the model quality and improving the accuracy of the model. So to decide how many principal components should we retain, we can follow these methods. Kaiser rule, break in slope, variance threshold approach. Kaiser rule suggests that component with eigenvalues greater than 1 should be retained, as they explain more variance than a single variable. So according to this rule, here we would pick the first 4 components. However, this rule can sometimes retain too many components when many principal components have eigenvalue just slightly greater than 1. Even sometimes can retain too low principal components. In such cases, we use script plot and look for a sudden break in the slope, also known as the elbow point. The break is visible here. It looks like an elbow point. Based on this script plot, here we would pick the first 5 components to represent our dataset. Variance threshold approach. In this case, we select components that explain at least a minimum amount of variance in the data. For example, if someone wants to retain 90% of the information from the original data, we sum up the explained variance of the principal components until the cumulative total is 90%. The first 5 principal components together explains greater than 90% of the variance. So we keep the first 5 principal components here. That's all for today. Thank you.